All right, everybody, welcome back from spring break. Hope everyone had fun and do whatever you guys do during spring break. Now we're, life is real, life is earnest. The next problem set is out. You've got 2 weeks. And we're gonna have a guest lecture today by our TA George, who's way more hardcore than me. And even though I offered him my slides, he's gonna do it on the board. So it's a real mathematician.
No slides. In fact, I don't really remember what's on the slides, so you guys have to help me recover all that knowledge. Maybe I'll ask some questions and you can respond with guesses and we'll work it out together. But yeah, we'll do more mechanism design today. And I guess, just wondering what was in the previous 2 lectures? What were the 2 topics that we looked at? Does anyone remember? People should volunteer. Yeah, okay, go ahead. Stable matchings was the lecture before the break, right? Or before the exam. Cool. Okay, and yeah, what's the rough setup of that problem? Someone else. Basically, don't give all the solution concepts or proofs, just what are stable matchings about at a high level? Yep, go ahead. Cool. Yeah. So preferences are given as rankings over the items, right? Nothing else that we would use to match them up. Okay. And 1 lecture before that, what was it? The first lecture on mechanism design by none other than Natalie. Yep. Okay. And what was the setup? So yeah. Yeah, perfect. Yeah, so people come in with their items and they basically start trading until everyone's happy. And sort of why both of these problems belong to this rough area of mechanism design is because we sort of care about maximizing some, socially desirable things about the eventual allocations. So this is different from the game theoretic things that we covered earlier, right? Because the game there was defined in a pretty set in stone way. Here we have to sort of set the terms of, or at least guide people towards how to optimally interact with each other to retrieve items that they like the most. So today we'll talk about a market model, not the market model because there isn't a single one. But what's yeah, give me a couple of words that are associated in your minds with the word market. Let's say market. Yeah. What are some related concepts? Somebody in this range classroom? Market. Yeah. Buying and selling. Okay. And to buy and sell, would you use currency? Money. Yeah, money. Perfect. So basically, there's still some items or goods, right? That we want to buy and sell. There's still people who are interested in getting those. So in that sense, it's similar to the top trading cycle setup that we looked at. And at the same time, it'll be different because in the top trading cycle setup, oh, that's much better. In the top trading cycle setup, everyone came with an item. There's no money involved. Everyone just trades according to the protocol that we give them. So the top trading cycle thing, right? In today's lecture, we'll look at a different model where money will be a factor. So it's not just about what you prefer, what items you want to have. It's also about whether you can afford them, right? So in that sense, we'll sort of get closer to a model of a market economy. Okay, so still mechanism design, but today we'll talk money, right? Okay, so what is the model? So still we'll have a bunch of buyers and a bunch of goods. So we have n buyers and we have m indivisible goods. So, and let's call the set of goods. So G. So what's indivisible? Indivisible means that, and G, think of it as a finite set, nothing fancy here. So G is a set of items, and each item can be had by one person or no people. So indivisible means that you can't split a single item between two or more parties. So that's not an option, okay? And will allow people to, like in the most general setting, to each receive one or more goods, or perhaps none, if they're not satisfied with the prices or the quality or whatnot. Okay, so let me also give another part of the model to you guys, and then later we can add on more stuff. So each buyer is assumed to have a valuation function. And this function will be denoted by VI. And once again, we want people to be able to get, no items, one item, more than one item, right? Entire bundle. So this function VI, the valuation, will map from SI into the interval 0, 1. So can anybody tell me, like in relation to set G, what's this bundle SI in set theoretic terms based on what we just talked about? So this is a valuation function for each buyer, takes in SI, a bundle of goods, and outputs a number between 0 and 1. Yeah, go ahead. Yeah, exactly. So where it maps basically all subsets of G, right? G is finite, so all subsets are just like a collection of 0, 1, or more bundles. Okay, cool. So there's that. And I mentioned money. So to introduce money, we can very conveniently assume that items have prices. Okay, so each item have a price, or good. Good J has some price, has price PI, or PJ. Okay, so this is the entire model of the market, pretty much. Now we need to decide on the next step, which is how do we describe the state of the market at any given moment? So what will it be? Like based on what we just defined, goods of prices, buyers want bundles. Yeah, they can have like one or more items and so on and so forth. So yeah, what, like out of the things that we just defined, like what's the state of the market fully given by at any given point? So suppose all of these objects already exist and people, have like bought what they need. Yeah. Okay. Yeah, exactly. So that's the first part of what determines the state. So let's do state. So state of the market will consist of, let's do allocation S. Okay, and S here will stand for the collection of SI for all I from 1 through N. Okay, so that's an allocation. Yeah, and what else do we need to know everything about the market out of all these things? So we need to know the prices, right? So P will be the entire price vector, okay? And why do we need to know the price vector? Well, each buyer has a valuation function. So like if the buyer just takes a look at all the items and tries, every single subset, the buyer will have some valuation for each of the subsets. But this does not include the money yet, right? So there's also the notion of utility, which is how I like a particular bundle minus what I have to pay for it. Okay, so that's the last ingredient, hopefully. And okay, so let's do 5 here. Actually, this is the state of the market. Okay, each buyer has a utility, and we'll consider a very natural class of utilities that are known as quasi-linear. yeah, the word quasi has an explanation behind it, but ultimately, it'll look linear to you once I write this down. So buyer's utility is defined as UI of a bundle SI and the price vector. And the definition is that we'll take VI of SI, the valuation, how much happier the buyer will become by obtaining the bundle, minus the prices. And we'll just sum up all the prices over all goods J and SI of EJ. Does this definition make sense? Okay, cool. Yeah. So this is the entire model of the market. We have states, we have utilities, we have prices, and now there's one point that we need to make clear right away. So the state of the market is described by an allocation and the price vector. So the allocation SI here, what do we know about it? We know that each SI is a subset of G, right? But we also know something else. So what else do we know, again, said theoretically, about any given allocation, right, that assigns a bundle SI to everyone? What do we know about sort of the relationship between the different SIs as subsets of G, given this discussion about indivisible goods? Okay, let's do you in the back row. Okay, potentially, although there could be goods that no one wants, right? Just too expensive or something. But yeah, that would be a good point. Okay, let's do it. Yeah, the sets are pairwise disjoint, right? So nobody can have any overlap because goods are not shared, okay? So let us call this a feasible allocation. Okay, S equals SI for all I and M. Feasible. Okay, it's feasible if SI intersect, or let's do SJ intersect SJ prime is in fact the empty set for all J not equal to J prime. Makes sense, right? So again, we don't require that S be a partition because partitions are required to, encompass the entire set G of goods, right? Whereas here, we allow for the possibility of certain goods just not belonging to any of the bundles. But the property that's preserved is that each good belongs to at most one bundle SI. Okay, so this is all the allocations that we care about. And once again, at any given price point, any allocation will induce a certain utility value for everyone based on their value of the valuation of their allocated bundle and the sum of the prices that determines the overall price of the bundle. Okay, cool. Okay, so we're doing mechanism design here. So what kind of bundles and prices, so what kind of market states would we think are desirable from a regulator's point of view? Doesn't mean we'll strictly enforce that, but we'll sort of guide the market in the right direction. So yeah, what do we want to happen? Anyone? Yep. Okay. So utility or potentially their valuations, right? So that's a good definition. And yeah, let me write it down. Okay, welfare maximizing bundle, social welfare, right? Bundle. Okay. So, okay, I'll define the actual value of the optimal welfare here instead of the bundle. But so opt will be the max value over all possible feasible bundles. So S feasible. And the social welfare of a bundle will be defined in a usual way. So for each I, we'll look at the I of Si, and we'll sum all of those things up. Okay, so this summation is a social welfare of any collection of bundles for everybody among the buyers, and then we take the max of that over all possible allocations. So good question. So if you wanted to optimize for the utility, you would have defined it that way. But if you want to talk about welfare and you want to talk about it in a price independent manner, right? Then you would define it like this. Yeah.
Could be another reason you might call this social welfare values you're including sellers some of the price paid to the seller. So some of the included sellers, including buyers.
Yeah. So prices, right? They're just like, part of the mechanism for exchanging your items. And so ultimately, like that's why this happens, that you sum up, both the utility of the buyer and the people. So prices here are just instruments towards achieving the ultimate goal of like matching people up with what they want to have. Okay. So again, very importantly, this definition is independent of the price vector. Just depends on the valuations V, not the utilities U. Okay. So that's one desideratum. Okay, and what other desirable states of games have we talked about early in the course? What else could be good to have? Yeah, okay, equilibria, right? And that's a different concept because for welfare, we just want everyone to be happy in total. And for equilibria, we are asking for a stability condition, which means that everyone's happy and no one wants to switch and screw over the current state of the economy, right? Okay, so equilibrium, and that's called Walrasian equilibrium. Walrasian equilibrium. Okay, named after Leon Walrus. It's an A, not a U. So that's the difference between the animal and the person. Yeah. So, and this is just one concept, right? So we're not talking about, like today's lecture will not, completely like, close off the topic, right? You can have like many such models, but like this is one of the most tractable and theoretically appealing models. And honestly, like I've looked through tons and tons of books, and everyone like gives like all these like sophisticated methods for computing Walrasian equilibria, and like to the point where they sometimes ignore like what real markets do, right? So real markets have like much harder equilibria happening. Sometimes no equilibria at all. Sometimes in the real world, everything's in a constant state of flux. Okay, so what is this equilibrium all about? So let me give you several conditions here. The condition number one, and this condition is it has some meaning behind it, and it's also like a very useful technical condition to have, is that, okay, first off, an equilibrium is a state, right? So an equilibrium will depend on both allocations and prices. Okay, so we will require that any item, any unmatched item, right? Any item not in anyone's bundle, item J, okay, has price EJ equals what's a desirable price to have for unmatched items from sort of like an economic point of view? Huh? The greater than the value that anyone could get from it. Okay, so this is actually, so this has its merits. It's actually the opposite of what we're going to set it to, which is 0. And the logic behind setting the price of all items that were not taken to 0 is actually that since the price of all the unmatched items is 0, right, the seller cannot lower the price of these items any further, right? It's already at 0 and still no one wants them, right? So that's the opposite logic. This logic, however, could also definitely make sense, okay? So this is condition number 1. Condition number 2 is just technical condition that S is feasible, okay? But like, this is not the main ingredient, of course. So for the main ingredient, yeah, I'm forgetting what's on the slide. So can somebody help me and sort of propose like an intuitive metric for what's an equilibrium state? So from the perspective of any individual buyer, what would happen in equilibrium by the nature of equilibria? So like, why did we define like Nash the way we did, and so on and so forth? Yeah. Okay, stable. So from my perspective, I'm one of the buyers. What does this stability mean? Yeah, cool. And in fact, we can go even more ambitious here, which might sound a bit surprising given that Nash just says, okay, you can like profitably deviate in this that way. So we'll basically require that the bundle that every buyer currently has in the state SP that we want to be in equilibrium state is almost or exactly an optimal bundle that a person could have. Okay, and in fact, let me say that we are actually defining epsilon Walrasian equilibria. Okay, so that we don't have to commit to exact optimality. So the definition of optimality here is such that for every buyer, okay, good. Everybody can still see this. Every buyer, or can everybody actually see this? Around like the 3rd row, 4th row. Yeah, cool. Yeah. Okay. So for all buyers I, we want to have the following, that the utility UI of SI is greater than or equal to what? UI of SI is at least, yeah. UI of SI prime minus epsilon. Exactly. So, and in fact, right? So we'll do it max, right? Max over all S prime feasible. Feasible. Perfect, right? So we take the maximum of like what could be available, right? Or in fact, we could literally just say max over all SI prime. That's a subset of G, right? Whichever you like. Okay, minus epsilon. So we're almost optimal. This is an additive notion of optimality. In fact, are you guys lying to me? Can you not see this from here? Always speak up. Yeah. If there's anything that you can't see, the best option is to ask me to move it. Yeah. Don't just stay silent. Anyhow. Okay, and this is literally the definition of the equilibrium. We're going to be finding it. Can you actually see it? Very important. Okay, you can see it. You can see it. Everyone can see it. Cool. Okay, good. Otherwise, like the rest of the lecture, you can just like basically like nap and whatnot and like not care because like that's literally what we're going to be like looking for. Yeah, perfect. See, okay, beautiful. Yeah. Okay, but like, yeah. Okay, so what do we want to do with this? We want to find this, right? And also want to find this, which is the welfare maximizing level. Yeah, go ahead. So utility is sort of like my trade-off. Like I'm a buyer. It's like my trade-off between like what I want to have and what I have to pay for it. So for a notion of equilibrium, it's definitely natural to use utilities. For here, you could again plausibly consider maximizing the total sum of everyone's utilities, but this is also a great objective based on like what we just discussed, like Aaron's point, and also that it ignores the prices. So there's like several desirable things about this, right? This is literally about getting the optimal thing. This thing basically almost makes us forget about the fact that prices ever existed, because ultimately all we want is to get people to be happy, right? Again, prices are just an instrument here. But for the equilibrium state, prices are a consideration, because if you end up paying too much for all you like, then you better switch out. Okay? Good question. Good question. Ultimately, many of these things come down to modeling, right? So ask these questions, and I'll basically say that it's just a model, and we'll move on.
Think about equilibrium as a general concept for everybody. I think the best way to do this is that both the sellers and the buyers are the players in the game. The buyers take care about their utility. The best response condition to the buyer is that they are buying the bundle that maximizes their utility given price. On the other hand, the seller cares about profit revenue. And so the fact that the unsold item has price zero, that's like a best response condition to the seller. If something is not selling and you would still have been happy if it sold at a lower price, you could lower the price. So the only way the seller can be best responding is if prices are zero. And then when we talk about social welfare, it's summing up over both the buyers and the sellers by price. These are really equilibrium conditions. Everyone is simultaneously best responding. The seller's utility function is the revenue they get, and social welfare is the sum for everybody.
Yep.
So is it possible to have two separate subsets of G where one of them has a higher valuation, but yields a lower utility for the buyer?
Yeah, potentially. Like if this is any concrete buyer can really value like a certain subset, like some types of candy over others, but they might happen to be like very expensive at the current moment in the current market conditions. So yeah, can definitely happen. And it's buyer dependent. Like the trade-off between how much you value a certain subset and like the prices is buyer dependent. The prices are there for everyone, but your valuations can change. So it could be that somebody very rich could actually grab something that's super expensive simply because the valuation is through the roof. Yeah. Yes. So there's this like implicit seller, right? And the seller wants to sell these items. In fact, there are also like other ways to model a market where people come with their own goods, almost like 2 lectures ago. But in this model, we basically assume that the items are already there, and there's a seller who basically wonders about how to set the prices on each of the items to, make the market equitable for everyone and like the market state to be good, right? So there's this implicit seller behind the scenes.
Confused about like how that seller structure though. Like in this one, it seems utility is inversely proportional to the prices and how we define utilities. I don't understand. Like what's the mechanism that makes the buyer given value?
The buyer gets their value through the valuation function, and the prices is what the buyer pays to obtain the item, and those go to the seller, which is like some entity sitting behind the scenes, right? So buyers get their value through this. They subtract off whatever they had to pay for it, and what remains is the net utility, right? By the way, it's not inversely proportional, right? It's like, it's not a division, it's like a subtraction. So you subtract off what you had to pay, and the seller receives all of those prices, like collects all the money that the buyers pay, right? And then what Aaron said is that you sum up all these utilities, right, for each buyer, and each item got sold at most once, right? And for all items that were unsold, the price is 0, right? So those items are fine, we can ignore them. And so we sum up all the utilities for the buyers, and then the utility of the seller is all the prices collected, right? So sum of PI over all items. And then when you sum up those two things together, you get the welfare. Yeah. See, a great question. P is determined such that we're hopefully here, or in both of these good scenarios simultaneously, right? So our job today is to actually find those prices, like find out how to set those prices, right? And like one way to approach this is a centralized approach, right? So an economy could just be, heavily regulated so that there's some centralized entity, right? It's like the party that sets the prices and says, every single good should be accessible to like every single person and so on and so forth, right? One way we could do it is we could like solve a huge optimization problem that would like look at like all possible allocations, right? And like look at all possible ways to set prices to make everyone happy, right? But we don't want to do that, right? We are, we live in a society where, we want to argue that like that's not the way to go in many senses, right? So instead, we want the prices to sort of set themselves, if that makes sense. And right now we'll talk about like what that actually means, right? And by prices setting themselves, so you all can provide input, but like the starting point of that is that if I'm a buyer and I go and try to like buy something from the market, then the price of that item that I'm trying to buy should intuitively go up if we were to imagine that like there are copies of items, for example, right? So that's how markets work. Okay, that's a way to think about it. So the market decides that things that are in high demand should have their prices go up. Okay, so and in some sense, what we'll do right now will be sort of we'll describe a way to do this by using a very simple algorithm. Okay, and this algorithm will hopefully satisfy many people in this room, and it'll hopefully not satisfy others because it's definitely not the most decentralized way to set prices. But it's a good and simple one. Okay, so I also forget what the algorithm is. So let me just say alg here. And let me just say that we start with everyone. So we'll have the algorithm will work to output prices. So pj for all items j, okay? And allocations. And the allocations, here we'll use this notation where mu is such a mapping that for every item j, mu of j will be bidder I who has j, okay? So that's what the algorithm will aim to find, both an allocation and prices, right? So the entire state of the market. Okay, so now I forget what the algorithm is, but the intuitive thing that we can do is to set all prices to 0. So p equals 0 means like every pj is 0, right? And mu of j is no one for all items j. Okay, and let me simplify this problem for us. Valuation functions, as we wrote them down over there, are actually quite complicated objects, right? Basically, you can have your own valuation for like each possible bundle, right? So in particular, the way we wrote down the model there could allow for things to happen where if I just get item 1, then I have a huge valuation for that. But if I have both items 1 and 2, then suddenly the valuation drops for whatever reason, right? And so this function can hide a lot of complexity if each bundle can have its own valuation in some unrestricted way, right? Instead, let's actually assume the following. And this is not, so we've defined like the most general model we could, but let's assume the following. Let's assume that for each buyer and each item, there's some valuation Vij between 0 and 1 that describes how much the buyer wants this concrete item. And let's say, to that extent, that for each I and j, Vi of Si will be equal to sum of these numbers Vij in 0 to 1, okay, over all j that belong to Si. Okay, so there will be numbers Vij for all I pairs Ij. Okay, does this make sense? That's a concrete model for like how we could view the utility function. For any buyer and like any subset of the items, each item has like a certain intrinsic value to that concrete buyer, right? Could have a different value to a different buyer. And then the buyer says, if I get 2 items, then I'll sum up their intrinsic value, right? So that's how you could think about bundle valuations additively, okay? Does this make sense to everyone? This is like the simplest, one of the simplest choices we could make for the valuation. Again, overall, the model does not say how complex the valuation functions Vi could be. They could be like potentially given by like many parameters, right? And like they could like treat like big bundles and small bundles differently, right? Could use different like rules for like how different people value them. Here we'll literally assume that there exists, so Vij is literally like n times m numbers, such that each of them describes for buyer I how much is item j worth. Okay, so but that's not the end of the story. We can simplify this even further, and we can say that buyers are unit demand. Unit demand. Okay, so unit demand means that each buyer's bundle has most one item. Okay, does this make sense? So basically, no one wants more than one item. In some sense, maybe like you go to a market and you try to buy 1 chocolate bar, right? You don't want 2 because that's too much sugar or more, right? And you can also go home with 0 chocolate bars if you want. Okay, so that's unit demand buyers. Cool. So can anyone give me an algorithm for how to solve this setting? See, I've simplified it for you guys as much as I could. Really don't remember like the actual thing. Let me just once again remind you all that this is where we start from. So the seller says all prices are initially 0. Everyone is initially unmatched, right? Absolutely no items used so far. No competition has happened, right? So try to remember what we talked about like roughly like 10 to 15 minutes ago in terms of like the intuition for like how markets set prices, and like propose maybe like a very rough outline of the algorithm, meaning like just a single sentence. What should the algorithm do? We start at all price being 0, which is the small, which is like the let's say the smallest they can be, and everyone is currently unmatched. What should we do? Any proposals? Speak up, otherwise I'll be sad. Yeah.
If there are still multiple buyers for the price is consistent enough, and then buyers either like drop off if they don't want to, like if they can't afford it, whether it's stay on with the price.
Yeah, great, right? So like demand determines how heavily priced a certain item is. You over there, was that what you were going to propose, or something different? Yeah. Mm-hmm. 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 Excellent. Yeah. So see, like together, you guys basically like covered some of the most important ideas of this algorithm. So basically, the seller will step away and just be like, yeah, you, the buyers, go ahead and bid on the items that you want, and I'll give you the items at the current prices, but then I'll raise the price in response to the fact that you just got them. So clearly you were interested in those items as your like optimal things, right? And once again, the unit demand model basically says that the bidding will happen, such that each buyer will consider like buying like a single item that's better than their current item. Okay, so it's a very simple setup. So out of the 2 lectures that happened before this one, yeah, does this remind y'all of anything? Any other model that we looked at? Unit demand buyers, valuations, Bij for each buyer and each item. Each buyer gets at most 1 item. Anything reminiscent of this? Yeah, stable matchings, right? So we could intuitively like, consider this picture. We have like n buyers and then goods, right? So there's these like buyers and the goods. And, there's an option for each buyer to either get matched to something, or for another buyer, they can like not be matched to anything. And, there's like something like this happening. Okay, so it's very related. Okay, does everyone see how this is very similar to the unit demand situation? Excellent. Okay, now my next question is, how is it different from the stable matching setup? Okay, yes. So here it's very possible that being unmatched will be the best option if everything that you want to get is too expensive for you to get it. Excellent. Okay, but another element of the model that's different between today and you over there, back. That could be a very useful assumption there. Here we literally don't care, right? If anyone likes chess, there's like a chess streamer that keeps saying that he literally doesn't care. So yeah, we literally don't care. Okay, you? Okay, good. Okay, so okay. What you're getting at here is that the model there was, really different in the sense that, there we just needed a ranking from everyone. Now we have, a whole lot more going on, right? Now we have prices in particular. In stable matchings, you could not buy your way into a certain preferable school the way you can, buy your way into a preferable item here. So actually matching up students in schools was, the model that we looked at before perhaps did not reflect, lots of aspects that are inherent to the US admissions system right now. Anyhow, so this also could be used to model some of that stuff. So we have money. Okay, so can we use deferred acceptance here? Not really, because we've slightly changed the representation of what we're doing, but okay. So let's not do it. Let me erase it. And yeah, since you all have given me so many helpful hints, now I actually remember what the algorithm is, and now I can write it down to some level of detail. So what happens is basically while there exists, and more than epsilon unhappy buyer I, right? Epsilon unhappy means that their actual optimal bundle at the current prices, right, which are initially set to 0, but they'll change throughout the algorithm, right? Epsilon unhappy is like a rough term that I use to mean that this buyer has their favorite bundle, and that bundle is better than the current bundle in terms of utility by more than an additive factor of epsilon. Okay, so we'll take any such buyer. Let me just say, like, while there's this like a buyer I prime, pick any such buyer I. Pick buyer I. Okay, we pick the buyer that's epsilon unhappy. Unhappy. Okay, and let this buyer look at item J prime, or J star, sorry. And item J star is the argmax of UI, and here I'll abuse notation, but most of you won't notice. UI of J, right? By the way, how am I abusing notation here in relation to the most general model notation when I'm writing UI of J? What am I abusing here? People do this all the time in like econ papers. So right now I'm writing UI of j, what should I write instead to make it compatible with this utility function definition? Yeah. So it's utility, right? So buyers care about their utility. So it is UI, right? And it is UI in relation to item j. So it's just a small like notational aspect. So it is morally the utility of I related to j. Okay, like take a look at how UI was defined. Like what was it defined with respect to? Okay, so first off, I'm leaving out prices. That's one notational flaw. Very bad. Also, SI is a set, okay? So instead of J, I should have written singleton, right? So just a set that contains J. Instead, I'm just writing J. Anyhow, very bad. You should always like, write this down in the prelims that will often abuse notation such that people read it and like they can't get mad at you because, you warn them that bad things will are about to happen. Okay, perfect. And this is argmax over all j. Okay, so we look at all items for that buyer, and we look at this. And by the way, what will this be? This will be basically Vij minus the current price Pj of that item, right? Cool. And then what do? We look at, first off, this utility, ui of j. So if you have here, is this utility guaranteed to be greater than or equal to 0, or is it not by how we define the model, like a priori? Uij, is this guaranteed the utility, right? Not the valuation. Is it guaranteed to be a positive number? We'll look at the very like desirable item, j prime, ui of j star, j star. Is it guaranteed to be at least 0 or not? Very simple question. Okay, somebody say yes or no and like justify, and we can argue over that. Yeah. They're potentially more than epsilon happy. Okay, good. That's a good reason. But if not for that, there could also be if this wasn't their favorite bundle, or if they weren't like epsilon happy or something, then it could be the case potentially that ui of j star could be less than 0, right? But yeah, as you say, if that happens, that's probably not for more than epsilon unhappy buyer because they have a desirable bundle. Okay. So basically, if the utility they would get from this j star is greater than 0, they will switch. And we'll say that mu of j star is I. Okay? Everybody remembers what mu means? Mu basically says that item j star belongs to this buyer indexed by this. Okay? Cool. And the price raising aspect is that P of j star becomes P of j star plus epsilon. Interesting, right? So first off, this item j star could have belonged to no one, at which point like its price would be 0 because it was never used before, or it could already belong to someone, some other buyer that had it. So in that case, we'll take it away from that buyer and we'll additionally raise the price of that item. Okay, sounds good? So price raising plus some buyers can become unmatched as a result of someone saying, oh, look, please give me this item. Like, I really want it. Like, really, like that's my like most favorite thing ever, right? Or that's my favorite thing ever. Who knows? Anyhow, you give people what they want, and you have to take that away from other people because items are indivisible. Okay? And the price goes up by epsilon. Epsilon is a parameter that we can set to eventually, hopefully, converge to epsilon Walrasian equilibria. So it's very suggestive notation here. Okay? So we have this algorithm. Can someone tell me from the perspective of the items that we have, what's true about items throughout this algorithm? So initially, all items are unmatched, right? What can we say afterwards? Yeah, what happens to item afterwards? Initially, all items are unmatched. Are there any invariants about items? And like, they're like, like people, yeah. Exactly. Perfect. Yeah. Prices never go down. So the beautiful proposal that says that prices can be adjusted upwards and downwards depending on what happens in the market. Here will not make use of the ability to drive prices down when it gets sold, simply because here we'll always essentially move an item from someone to someone else who wants it even more. So here it'll make sense to do essentially an ascending price auction, okay, where prices always go up. And moreover, every item that gets matched is never unmatched again because someone already likes it. And in fact, that someone, when they got that item, like it very much at the current price point, the most. Perfect. Okay, see, beautiful. So there are some subtle relationships here to the deferred acceptance algorithm, but there's also differences, of course. Excellent. Okay, so how do we analyze this? First off, let me remind you guys very suggestively that each Vij, so the valuation that everyone could have for their favorite item, is always between 0 and 1, very suggestively. And now let me ask the following question. Does this thing converge in finite time? So I fix an epsilon equals 0.1. Will this thing converge in finite time, or like has it some potential for diverging? So keep matching people to their favorite items and take items away from previous owners and give them to next owners and raise prices and so on and so forth. Yeah. Perfect. Yeah. Prices always go up. So epsilon, like it's small, but it's not too small, right? It's some fixed amount. We have to commit to it. We can't just like say that like epsilon is like infinitesimally small. That's a different area in math. Like here, we want epsilon to be some concrete amount. And in roughly 1/epsilon rounds, each price will reach its like highest point, 1, at which like no one wants to get it, right? Because the valuations were between 0 and 1. So yeah, perfect. Okay. Yeah, let's actually get a slightly more precise bound on the convergence time of this. So yeah, actually, so I kind of forget what that proof was all about, but one thing that I remember is it says something about how many items. So how many items out of m items, right? So someone mentioned that here m is not constrained to be anything in relation to n, right? So we have n buyers, and they're doing this matching process. So by the definition of our model, how many items will like ever get matched and stay matched consequently? N buyers and m items, yeah? Up to n items, right? And each of them has price at most 1, right? Okay, so we should always look at, when we're analyzing an algorithm, we should look either at a potential function or like either an invariant or a semi-invariant, right? In this case, we have this quantity, which is sum of Pj for all j in the entire set G, right? So all prices and all items in the market. And that thing cannot ever go above n. And each round, we raise the price of one of them by epsilon, okay? Okay, so someone, maybe like from that side of the room, probably someone who hasn't spoken up before, yeah. Can someone tell me what that implies about like how many times in total price, any price will go up? Implying, that this is, the number, that like max total number of rounds that this algorithm will go through. Yeah, someone from like roughly like over here. Again, I remind you that in each round, one item, like while the algorithm still goes on, each item gets sold to someone new and its price goes up by epsilon. And I also want to remind you that the total number of items is at most n, and the final price of each item is at most 1. So piece that together and tell me, yeah, what's the number of rounds? Maybe you? Perfect. Yeah. N over epsilon, right? See, like I basically, like, I didn't remember if it's like n over epsilon or n over epsilon squared or something like that. So, yeah, now we know, right? N over epsilon. So again, to get a sense of the scale, by the way, since we used to do like regrets and whatever. Yeah, go ahead. It was, and then we argued that the total number of items ever assigned to anyone that get involved in this process is at most n, because each buyer has at most n item, or 1 item, right? And no item ever goes unmatched, right? And then each of these items has like price at most 1. So we sum them up and get total price at most n. To reach that price, we need to do n over epsilon iterations. So, okay, we used to do regrets. So is this bound better or worse than n over epsilon squared, for example? Just like a quiz question on your final. Is this bound that we actually got better or worse than this bound? Which one of these would be better? Interesting. Yes, that is correct. So if epsilon is 0.1, good. You plug it in here. That means you get 10n, right? But here you would get 100n, right? Okay, so this is like very useful for like sanity checking your regret bounds and so on and so forth, like runtime bounds. So yeah, but let me raise this to not confuse anyone who's been maybe like catching it up or something. So this is the actual answer, right? Like, yeah, this is the runtime. Perfect. Okay, so we have this nice algorithm and it converges and it drives prices up and so on and so forth. So why did we do this exactly? So what was this algorithm supposed to find for us? Why did we run this algorithm? To determine like prices and like allocations? And like when it stops, we obviously output the current price vector, right? And the current, set of bundles that each buyer receives. Like, what is this for? Like, are we just analyzing, some, subroutine for something bigger, or, is that it? Is that what we want? So what did we want? What were our desiderata from half an hour ago? Yeah. Exactly. See, like, because we talked about it like 30 minutes ago, this, is already like out of our focus, but that's actually what we're working towards, right? Right now, we just showed that we can like, allocate items to buyers and settle on a price vector. And very clearly, when this algorithm is not going anywhere anymore, that means everyone is epsilon happy, right? So that's kind of good. Doesn't that mean that we are at a Walrasian equilibrium? So can somebody argue this for me, semi-informally? No need to write anything down. Also because you can't, you can just say things. Yeah, okay. Again, yeah, anyone from this corner that's not one of the people who have answered questions before? Anyone? So, okay, we're trying to find a Walrasian equilibrium, right? A Walrasian equilibrium is such a state where everyone is almost happy, other than like an epsilon additive factor. What does that mean? Yeah, additive constant. Okay, and we assign and reassign people to their favorite items until this process converged, and now everyone's epsilon happy there. Okay, so what else? We still have 2 other conditions in the Walrasian equilibrium definition, right? Which are easy, but still, someone needs to sort of like talk through these conditions. Okay, anyone who hasn't answered before? Yeah. Mm-hmm.
And then we know that any unmatched item on price 0 set on 0 at the start.
Mm-hmm. And they never get matched, right? Because when an item gets matched, it can't get back to unmatched. Cool. Excellent, right? Very easy. I just gave you the algorithm and suddenly there's a proof that it leads to a Walrasian equilibrium. Isn't that cool? in particular, what's really great about this is that everyone is basically at their most preferred point, granted, given the current prices, right? Because its utilities are relative to what the current price levels are, right? But at those prices that are currently set in stone at the end of the algorithm, everyone is almost happy, and the degree of like almost happy, we set it. We set the epsilon.
Isn't it possible that like items should be matched to people because the Walrasian
So here we said, first off, here we said that each person is unit demand. So no one wants to have a second item. So really the only option at the end of this algorithm could be if someone wanted an unmatched item in exchange for their current item. But because we define like an unhappy buyer as a buyer who doesn't like their item at the current price point, then it can't happen, right? So, if you could say like maybe for some buyer, like the price of the item is very, very large. But by definition of the algorithm, if they still have that item, that probably means they have a very high valuation for that item, right? Again, could be a very rich person wanting to get a very luxurious mansion, right? Somewhere in Orange County. Yeah, and like, they could get like another house for free, but like, who cares, right? They have the money, they have the means, which is reflected in their evaluation, right? Okay, perfect. Okay, so what have I not talked about? Like, I'm forgetting, like I defined so many things. Anything else that we haven't talked about physically obtaining? Yes, someone who hasn't answered any questions before. This is a very easy question. Which of the items that we just wrote down on the board, like, have we not addressed as of yet? Someone. I'm stubborn. I'm just gonna keep waiting. We wanted a couple things. We got one of them, which is the Walrasian equilibrium, right? Or an epsilon approximate Walrasian equilibrium. Okay. Someone else, yeah. Yeah, exactly, right? Maximum welfare. Okay, so do you have a guess of like how we would get it if we wanted to be lazy? Like, let's say I don't want to give any more algorithms to you. Like I already gave you an algorithm for computing an epsilon Walrasian equilibrium, right? So if I'm lazy and I want to do like any extra work in that algorithmic direction, what will I do right now? Okay, so you're saying you take the Walrasian equilibrium, right? And you try to show that it's what? Or approximately maximum, right? Because we just got an epsilon Walrasian equilibrium, right? So the maximum will of course also be like not exactly, but approximate. Right, perfect. Okay, that's what we'll do. Okay, so so does anyone have any preferences for what to raise here? Is everyone happy with the algorithm, or do we want to keep going with that? Yeah, we probably want to keep going that because I still have a point to make about it later. Maybe this thing? I don't know what this is about. This was like about like whatever runtime bounds. I forget, right? Raising this, everyone happy? Everyone knows how long this thing will run for. Importantly, does everyone like have a firm grasp on why this thing will at least converge in finite time? Cool, excellent. Okay, I'll trust you. So the next lemma will show. Actually, let's say that it's a theorem because it's pretty important and cool, right? So we wanted a stability condition, which is called Walrasian equilibrium. But actually, we're also getting welfare maximization for free. Because let's say that S comma P is epsilon Walrasian equilibrium. Okay. Then S. Let me actually write down the welfare very suggestible over all buyers of Pi of Si, right? Where Si is the bundles that S is formed of. Okay. Is at most. Yeah. What is it at most? Yes. Someone give me some approximate expression here. Take a guess. So I gave you an epsilon Walrasian equilibrium, which I'm trying to show intuitively that it's also like almost like a welfare maximizing state. So I just wrote down the welfare of the allocation in this equilibrium, right? Didn't mention anything about the prices just yet. What's on the right-hand side? So the welfare in the Walrasian equilibrium. Yep, you. What minus epsilon? N? Okay, so that's a good guess, but it's a bit too optimistic, right? Because it's definitely not like valuations can be different. Maybe all valuations are like very small, so you can't get all the way to 1, right? Maybe everyone's values for every item are like 0.1 or something. So then you can't get to n exactly. But okay, so let me do max here. Okay, can someone complete it now? The valuation, the social welfare in the state S is at least the max. Look over there, definition of welfare maximizing. Yeah. Yeah, minus something that depends on epsilon, right? Perfect. Yeah. What's that thing? Oh, max. Let me call it S prime, right? Because S is already taken as the equilibrium thing. Okay, max over S prime of sum of, yeah, VI S prime I. Perfect, right? Minus, actually, the thing here will be minus epsilon n, where n is the number of buyers, okay? So the bound will be good, but perhaps not as good as you might have wanted it to be, okay? So if we have 1,000 buyers, that means that we want to, oh, that's okay. If we have 1,000 buyers, that means we want epsilon probably like something like 10, like 1 over 10,000, right? So we want to get like really close to the Walrasian equilibrium to make it close to the optimal welfare. Okay. Yeah. So this is the whole max thing. This is minus epsilon n. Okay. Cool. Okay. So to save time a little bit, yeah. Go ahead. Over here. So what's important to understand is that welfare maximizing bundles, right? Once again, were defined with respect to the valuation V, right? Yeah. So not like they did not involve anything regarding U, right? So the prices play no role here. So now I think you're confused because you're saying the Walrasian equilibrium that we defined has U's in it, right? But somehow I'm claiming that we can deduce something about the total sum of the valuations, right? So there seems to be a mismatch, right? Right. Once again, like going back to the discussion at the beginning of today's class, right? This thing is given through the V's, which is the intrinsic valuations, don't depend on the prices. And stability in the Walrasian equilibrium case is afforded, with respect to the utilities, right? So that means that what I'll show you guys right now will sort of like factor these prices back out, right? In some sense. So what I'll do is I'll write out the definition of Walrasian equilibrium for every single buyer and then some overall buyers. This is a good technique, which you might or might not need on some homework. But again, so I'll write down the Walrasian condition for each buyer, I. So for all J, yeah, okay. In fact, each buyer I gets their item, right? Which I call SI, but that's a single item, right? So SVI of SI, again, single item here, minus, okay, fine. Okay, I'll do VI of J, okay? Of J sub I. VI of J sub I minus P sub J sub I, okay? So each I gets J sub I, which could be an item or could be like no item, right? It could be like, an empty item. Okay, so this thing, okay, is better than anything else they could have had. In particular, let me take any other arbitrary feasible allocation SI prime, which would basically do the following. You would get VI of J prime of I minus P J prime of I. Okay, so I fix S prime, which is given by J1, J2, Jn, right? A single item or an empty item for each person, right? Prime, J prime 1, J prime 2, J prime n, right? Meanwhile, S, which is the Walrasian allocation that we are trying to say is optimal with respect to that, is just J1, J2, Jn, okay? So two allocations. This is the Walrasian allocation. This is any other allocation, okay? And the price vector is set, right? It's this one. Okay, so I have this happening for every buyer. Does everyone agree with this? I just like wrote down their condition that they're happy here, as opposed to any other state. Or did I make a mistake there? Maybe I made like a slight inaccuracy here. I claim that I just wrote down the Walrasian condition for each buyer in like allocation, like where they get Ji, as opposed to any other allocation where they get Ji prime. Yeah? Yeah, I did not include the epsilon. Guess what? That's the epsilon here. Okay, so now what do they promise? That I'll sum up over everyone, okay? I'm summing up over everyone. Very useful trick to deal with Walrasian equilibria. All buyers I. And here I'm also summing up all buyers I. To be clear, I'm summing up the entire left side and the entire right side, right? I summed up a bunch of inequalities. Inequality is still true when you sum it up. Excellent. Okay. So in particular, summation still extends to over here, right? This entire thing gets summed up. Excellent. Okay, so let me rearrange it. And to rearrange it, I'll rearrange it as follows. So sum of Bi Ji over I is greater than sum of Vi J prime I over I minus epsilon n plus plus, and here I'm going to do the price vectors, right? So P J I prime, okay, minus P J I over I. Okay, so can you all pattern match this and what we're actually trying to show, which is this? So, right? This is what we just got by summing up a bunch of Walrasian conditions over all buyers. This is what we want to show, which basically says that the Walrasian equilibrium allocation is almost the welfare optimal allocation, right? I just wrote out this goes here, this goes here, and this is an arbitrary allocation, J prime, right? So it's the same as like saying that it holds for like the max over all possible allocations J prime. This epsilon n, and there's this extra term, right? So this extra term, we hope, is, how does it compare to 0? Check the time. And why? Okay. We're summing up all prices in the state S, which is the Walrasian allocation, which is Pji, and we're also summing up all prices in Pji prime, right? The price vector is the same though, okay? So in both, for like we're comparing two allocations here, S and S prime, but the price vector is the same. So the only thing that changes is which items belong to who. But the summation of the prices, right? If you take it over every bidder, intuitively shouldn't really change that much, right? We have a common price vector, which is the Walrasian price vector, right? So that price vector determines the prices allocated to everyone. And an alternative allocation S prime would just like reshuffle which item goes to whom, right? So intuitively, what does that say? Very interesting. Okay, anyone? We have S comma P, okay? That's an epsilon Walrasian equilibrium, which means everyone is epsilon, at most epsilon unhappy in that current state, given the allocation S, which gives them ji to each buyer I. Okay. And I wrote this out to say that for any other arbitrary allocation where everyone gets ji prime instead of ji, they are potentially just more unhappy, right? Other than a factor of epsilon. And then I summed the unhappiness up over all buyers. And I moved things around. And now I'm comparing the sum of the prices pji prime over all I and pji over all I. How do they compare? Mm-hmm. Mm-hmm. Yeah, exactly. So again, to recap this, we set the prices. All we know is that from the Walrasian condition, everything that's not assigned to anyone in the Walrasian equilibrium, right, for allocation S, all of those items have price 0, right? All the items that have non-zero prices are matched. So all JIs, together make up like all of the prices, okay? Meanwhile, if you reassign items, then either the same items get reshuffled and all items that have 0 prices are still left alone, right? Or we leave out some items that are priced above 0 and bring in some items that are priced at 0, okay? Does that make sense? That is actually where the condition that all unmatched items in the Walrasian equilibrium have price 0 come in. So like those items are not desirable. And in particular, if you fix the prices and do like any other allocation, then the total price paid to the seller of that allocation could only drop if we accidentally leave out items that had non-zero prices. Yeah. So what happened here, which is a miraculous thing, is that when we talked about welfare maximizing bundles, we just talked about bundles and valuations, right? We didn't talk about prices. Prices could be anything, right? We just want to look at the final allocation and look at how happy people are without taking into account their like prices, right? That made them get to that point. Meanwhile, Walrasian equilibria do require us to reason about prices, but we summed up a bunch of Walrasian conditions over all buyers, and the entire thing with prices went away, right? So this thing completely went away. Prices canceled out and disappeared essentially because of the condition that every unmatched item in a Walrasian equilibrium had price exactly 0. So eventually, what do we conclude to your question? We conclude that the Walrasian equilibrium allocation is almost the optimal allocation, regardless of what the prices were that took you there. A Walrasian equilibrium is a tuple that consists of the allocation and the prices. So the prices, think of them as like a technical tool to get us to the right allocation. And so what we showed, which is a pretty cool thing, is that we got to an optimal allocation by using some prices. And how did we set those prices? Well, if we use this algorithm to get to the epsilon Walrasian algorithm, then that's how the prices were set, right? So these prices got us there to some allocation. And then we took that allocation and said, well, here were the prices, but at these prices, comparing our allocation to any other allocation cancels out the prices. And then what comes out is a statement just about the valuations and the allocation. Okay? So that's a very cool fact. So in fact, one of the main takeaways besides this algorithm of this lecture is this link here. Okay? If we have an epsilon Walrasian equilibrium, or rather, actually, this link, right? So I didn't show that if you have a welfare maximizing bundle, that it's also an equilibrium bundle, right? But what I did show is that if we get stability, we also get approximate optimality, right? So epsilon Walrasian equilibrium translates into an epsilon n approximately best allocation in terms of welfare. Great question, right? So we assume unit demand. This algorithm, which got us to the Walrasian equilibrium, assumed unit demand. Now, when we proved that equilibrium implies welfare maximization, what we did here did involve the JIs. But if you later check the slides, you'll see that that calculation actually does not need to assume that we are unit demand. Okay, that calculation holds even when buyers can have different, like various items in their bundle, right? So we could replace here JI by SI and J prime I by S prime I. Okay, so the fact that Walrasian equilibrium imply welfare maximization is still good. Okay, so the only thing that's not good is the algorithm. And in the remaining couple of minutes, let me tell you what to do when we don't have this crazy restrictive unit demand condition. In particular, maybe like items in the market are heterogeneous, right? Which means that it's not like we don't just need like one chocolate bar. Maybe we also like get like other stuff, right, at our local grocery store. Okay, so their unit demand will not work because we need chocolate bars and we need sanitizer and like, you know, we need something else, lotion, who knows. Okay, so what matters here, yeah, actually what mattered here? What mattered here? How did we use the unit demand condition that everyone can own at most one item? Like, give me like a way for how this was used. That everyone can own at most one item. Like, why was this useful? Uh-huh. Cool. Uh-huh. Excellent. Okay. There's the and let me give you the definition of the most general types of demands for which we can also achieve that. So this will be called gross substitutes. Substitute. Okay, so gross substitutes means the following. So consider two price vectors, P and P prime. Okay, two price vectors. What do I mean by, you know, one vector is less than equal to another vector? That each coordinate of this vector, each price Pj, is at most price Pj star for the same item in the other price vector, right? So prices could have only gone up, which is in fact true throughout this algorithm, right? Each price like individually goes up for each item. So price vectors can only grow in this sense. Okay, so let's consider any buyer. So, and this property is a property of gross substitute. So like VI satisfies this property. So for every I, let's consider their best bundle, S prime or S star here in the vector P, S star P. Okay, so this bundle has a bunch of things in it. So the things in particular are some items, right? Maybe like, you know, like a bunch of J's, right? Like, I don't know, J1I, J2I, etc. Okay, so now some prices went up and some prices stayed the same. So we got to P prime. So now you have S star P prime. And I'm assuming here that there's like a single unique optimal bundle for everyone, right? But of course, like usually, like it could be that it's a couple of them like having like the same value, right? So here I'll just assume that the argmax contains a single bundle. Okay. So what do we want about this SP prime star? We want it to only expand. So we still want to have S star P union some more items. Okay. What that means is that prices go up. I consider any concrete buyer. That buyer has these items, and that buyer now says, actually, prices have gone up. So now my optimal bundle has changed, right? It would be a pretty bad scenario for us if that buyer suddenly wanted to switch to another bundle where some items would be dropped, let's say, right? So really what we want and what gross substitutes, and this is a property, right, of the valuation functions, right? Here, the unit demand valuation function says that it only values at most one item to like some extent. Gross substitutes includes that and more potential valuation functions of this kind, right? So this property gross substitutes was important here. In fact, the same algorithm will be cool again. All that's changed is that now everyone can have like an entire bundle of favorite items. But because of the gross substitutes condition, those items that were in that bundle can stay there, and more items can be added on, right? Okay, so that's the slightly finer point, which basically says, okay, unit demand made it easy, but we can also go more general. And maybe like on some homework, we might ask if the gross substitute condition, is satisfied for like some other class of valuation functions or not. The exact definition will be in the slides to double check, right? But one way gross substitute is useful in mechanism design is it allows us to extend simple algorithms that we initially derived for simple things like I want at most one chocolate bar to more complicated bundles and more complicated valuation functions for the bundles. Okay, cool. Okay, so to summarize, we went over a market model, and we showed that we can do welfare maximization and equilibrium all at once by using a relatively simple algorithm for a relatively simple class of valuation functions. And what we briefly mentioned is that some more complicated valuation functions basically require the same algorithm, but slightly adapted. Okay, thanks.